Now that the trial section of the plate girder for our steel trussed bridge is ready, we have designed, this is the plate girder, trial section of it. The trial section for the designing of the cross girder for our steel truss bridge is ready. We have adopted the flange plates of width 400 mm and thickness of 25 mm, and we have adopted the web depth of 1000 mm and the thickness 10 mm. All right, now this is the trial section of the plate girder. For the cross girder, we are designing for our steel truss bridge. We have designed the deck slab, we have designed the stringers. Now we are designing the cross girders, and it's already been discussed that the cross girders in case of a steel truss bridge are designed as plate girders, and the trial section of the plate girder to resist the moments and the shear forces that are going to come over my cross girder. This is the trial section. We have designed it as per the moments and as per the shear force. Now we have to, by adopting the different depths for the web and the flange. For example, in here, we have adopted the depth for the web plate as 1000 mm and the thickness as 10 mm. And for the flange plates, we have adopted the width of 400 mm and the thickness of 25 mm. All right, now this is our trial section of the plate girder. For the cross girder we are designing, we have to now check it for the various stresses. If it passes the various stress test, then it's okay and safe. Otherwise, we have to go and we have to redesign the section. Now we will have various checks. The first one being check for maximum stresses. Check for maximum stresses. We'll be checking it for A, flexural or bending stresses, and B for shear stresses. All right, so we have to check our trial section of the plate girder that we have chosen for designing the cross girder of our steel truss bridge. We have to now check it for various stresses, flexural stress and the bending stress, and shear stresses as well. Now one by one we'll be checking it. Let us first calculate the moment of inertia. Moment of inertia of cross section. Moment of inertia of cross section of the girder about the x-axis axis. All right, we'll calculate Ixx. In case of these are rectangular sections, both flange plates as well as this web area, and we know that the moment of inertia of a rectangle about x-axis axis is how much? Here x-axis axis is this is the y-y axis, x-axis axis, y-y axis. We have to calculate the moment of inertia. We'll be calculating moment of inertia about both the axes, x-axis axis as well as y-y axis. Moment of inertia of a rectangle about the axis passing through the centroid is given by, it's given by bh cubed by 12. But please note that this is the moment of inertia of a rectangle about the axis passing through its centroid, where b is the width and h is the height. If we have to calculate moment of inertia of a rectangle about an axis passing through its base, that will be given by bh cubed by 3, where b is the width and h is the height. And if we have to calculate the moment of inertia about centroidal axis perpendicular to its base, this was about the centroidal axis, and if we have to calculate about the centroidal axis perpendicular to its base, it will be given by hb cubed by 12. All right, so this was about the moment of inertia of a rectangle about various axes, centroid, base, or perpendicular to the base about the centroidal axis, this one. All right, now we'll be calculating Ixx first. This is the x-axis axis. All right, and this will be the base and this will be the depth for the sections. Now we'll calculate Ixx first. All right, now let's solve. and calculate the IXX. For example, I'll consider this as a bigger rectangle. Please allow me to show some hatched portion over here. All right. Consider this as an imaginary hatched area. So this is the bigger rectangle, and then this is the smaller one. If I'll consider this whole, this is the big rectangle. Then if I'll subtract this much, the hatched area, then I can get the moment of inertia of my I section. See how? IXX, first of the complete rectangle. Please note how much? It is 400 multiplied by, this is the base. How much is the depth or height? This whole. If this is 1000, this is 25, this is 25, this is the distance from here to here is how much? 1050 cube by 12. All right. See carefully. I have calculated the moment of inertia about the x-axis of this whole rectangle. All right, with base of 400 and the depth of 1050. All right, breadth 400, height 1040. 1000 is the depth of the web plate, and flanges we have 25, 25. So the total will become 10450. All right. So this is the moment of inertia of this whole rectangle about the x-axis. It is given by ph cubed by 12. But from this, to calculate the actual moment of inertia of my I section, I have to subtract which area? This area, hatched area. This and this. Now let's see what is the moment of inertia of this hatched area. I'm unable to show complete hatching over here. But please note, this is this whole rectangle excluding this part, excluding the web plate of the I section. I have calculated the moment of inertia of this whole rectangle. Now I'll be subtracting this portion, and then I'll be having the moment of inertia of the I section. See, what is the base of our this hatch section? It is again how much? From here to here it's 400, but I have to subtract the web part. How much is the thickness of the web? It's 10. So this is 400, this is 10. So the remaining portion will be 390. From here to here and then from here to here. All right, 390 bh cube by 12. How much is the h? H is 1000 for our hatched portion of this rectangle, excluding the web plate. This is 1000 cube by 12. All right, by calculations, moment of inertia of this I section about the x-axis is how much? It is 61 into 10 raised power 8 mm raised power 4. All right. So this is how I calculated the moment of inertia of the cross section of the girder about the x-axis. I first calculated the moment of inertia about x-axis of this whole rectangle. Then I subtracted this part, and then I got the moment of inertia of my I section. This is how I did it. All right. Let me drop it first. So this is how we proceed with the designing of our cross girders. We selected one trial section, and now we are checking this trial section for various stresses. First, we'll be checking it for bending and shear stresses. All right. So now I calculated my moment of inertia of this trial section of the plate girder about the x-axis, and this came equivalent to how much? 61 into 10 raised power 8 mm raised power 4, because every dimension was in millimeters. All right. Now the maximum actual maximum bending stress is given by sigma BC, and this is equal to my divided by Ixx. The actual maximum bending or the flexural stress for this trial section of the plate girder is given by sigma BC, and which is equal to m multiplied by y divided by the moment of inertia of this plate girder, but about which axis? The xx axis. Alright, now let's calculate the actual maximum bending stress first. Sigma BC is how much? Moment. These are my design moments. How much were these? When we calculated the design moments, the total design moments was how much? It was 1672 into 10 raised power. Our total design bending moment is 1672 kilonewton meter. So let us take 1672, but for the sake of dimensional homogeneity, because the unit is kilonewton meter and we have here dimensions in newtons and mms, so into 10 raised power 6, this was our design moment on which we designed or selected our trial section of the plate girder, multiplied by y. This is the depth of the neutral axis. All right, this is how much from this? It's 525. This is the depth of the neutral axis or the xx axis. But from where? From the top of the flange. If this is 25, this hole is how much? This is 1000 mm. So from here to here it's 500. Then from we have to add the thickness of the flange, that is 25. So from here to here we have 525. This is y. And then Ixx, how much did we calculate it? 61 into 10 raised power 8 mm raised power 4. All right. So our actual maximum bending stress that this plate girder will be carrying is how much? By calculations, this is 144 Newton per mm square. All right, this is 144 Newton per mm square. This is the actual maximum bending stress that this plate girder, the trial section of the plate girder rather, which we are taking for designing the cross girders of our steel truss bridge is how much? 144 Newton per mm square. Now the permissible bending stresses corresponding to the elastical critical stress, let me write it down first. This is how much? This 144 Newton per mm square is the actual maximum bending stress this will be carrying. Now we have to, for checking the section for the flexural or the bending stress, we have to compare it to the permissible bending stress that is allowed for this trial section of the plate girder. We have to now calculate that, and that is a lengthy process. Let me rub it first. We have calculated the maximum actual bending stress it will be carrying. Now permissible, since we have to check the section for the stresses. Now permissible bending stress corresponding to elastic critical stress for yield stress of how much? Rolled steel sections having a yield stress of 236 Newton per mm square are given by IRC 24, the Indian Road Congress codes. We have a table over there. But for that, we need to calculate this thing first, the elastic critical stress. See, I'll show you the table. This is the table. All right. This gives us the actual or the allowable working stress for different values of the critical stresses, conforming to the yield strength. This is 236 Newton per mm square. This is something else. But in the question itself, it is given that you have to use the rolled steel sections with yield stress of how much? 236 Newton per mm square. And this is the table given in IRC 24. From this side, you can see this is the critical stress or the elastic critical stress in Newton per mm square units. And this is the sigma BC, the permissible bending stress for the yield stress of 236 Newton. What we calculated 104 Newton per mm square was the actual maximum bending stress that is going to come. All right. Now we have to see what is the permissible or the allowable working stress as per the IRC, and that should be less than this allowable or the permissible one, then only my section is safe. How do I need to calculate this? As per the IRC 24 table, which will give me the allowable working stress or sigma BC or the permissible bending stress for the yield stress of 236 Newton per mm square, which I am having for my rolled steel section for the various values of the elastic critical stress, which is given in this column. But that to match it, what do I need to calculate first? Then only I'll see from the table what is my allowable working stress or what is my permissible bending stress for my yield stress of 236 Newton per mm square for the different values of the elastic critical stress that I am having. But for that, the first and foremost step is to calculate the elastic critical stress for the I sections. And the elastic, since as already discussed, and we are discussing it every now and then, that we are designing our steel truss bridge as per the working stress method or the elastic design method. All right, so the elastic critical stress according to IRC 24 for I sections. This is our I section. For I sections is given by this is the elastic critical stress denoted by C. S is equal to, please note the formula, 2677300 divided by L by Ry square of it multiplied by 1 plus 0.05 L multiplied by T C divided by Ry D square of it whole raised power 1 by 2 Newton per mm square. So by adopting or employing this formula, I'll be calculating the elastic critical stress according to IRC 24 for the I section that I'm having, which has the dimensions like mentioned in this figure. All right, so this is the formula. Now in this formula, please note that L is the effective length of the compression flange, Ry is the radius of gyration, D is the overall depth, TC is the effective thickness of the compression flange. All right, so every term is hereby denoted. Let me repeat once again. L is the effective length of compression flange. Ry is the radius of gyration. D is the overall depth of girder, and TC is the effective thickness of compression flange. If we know all these things, we'll be calculating our elastic critical stress. Then from the table, we'll be having the permissible bending stress or the allowable working stress. And that should be what? The actual bending stress should be less than the permissible stress. Then only my section is safe. Again, is the bending stresses or the flexural stresses. All right. Now let's calculate this thing first, the elastic critical stress. And let me rub it first. Step by step, we are learning the process of designing of the steel trussed bridge, and simultaneously we are also learning the steps of designing the plate girder bridges. because plate girder is the same thing. Cross girders in case of steel truss bridges are designed as plate girders. Alright. Elastic critical stress 2677300 divided by L divided by Ry square of it 1 plus 0.05 L TC R y d square of it 4 raised power 1 by 2, and the units will be Newton per mm square. Alright, now let's see how we'll calculate this thing. For that we need various things. The first one being is the radius of gyration. Radius of gyration or radius of gyration, howsoever you may like to pronounce it. It is given, it is denoted by K, and it's given by, must be knowing, it is under root or the square root of I by A. For any section, radius of gyration is given by the square root of moment of inertia divided by area. Now the question arises, moment of inertia, which moment of inertia? Have we to take moment of inertia xx or the y axis? Alright, is this ixx or iyy? But let me tell you, it is iyy divided by a. We have to take, for calculating the radius of gyration, we have to take moment of inertia of this trial section of the plate girder about the y axis. And let us discuss something about the radius of gyration first to have a quick recap of the concept. What is radius of gyration? Radius of gyration tells us how far from the centroid the area is spread out. Radius of gyration, or the K, it tells us how far from the centroid, the area is spread out. All right, and a higher value of K generally means a more stable structure against buckling. A higher value of radius of gyration means that our structure is more stable. Structure is more stable against buckling. All right. So this term, the radius of gyration, it tells us how far from the centroid the area is spread out, and a higher value of radius of gyration means a more stable structure against buckling. And the axis you use for calculating radius of gyration depends on which axis you're analyzing the object's rotation or bending about. And the stability analysis about particular axis demands moment of inertia from the same axis to calculate the radius of gyration. And if I'm saying that we are calculating radius of gyration about the y-axis, that means this is the axis we are using to calculate radius of gyration, because this is the axis we are analyzing the object's rotation or bending about, and the stability analysis will be taken from the same axis, the y. So in this trial section of the plate girder, I'm using my y axis to check or to analyze its rotation or bending about. That means stability analysis about the same axis I have to take to calculate my radius of gyration, that is the y axis. All right, so first step to calculate the elastic critical stress is that I have to calculate my radius of gyration. All right, and I'll be calculating the radius of gyration about the y axis because I am interested to know about, or rather I'm analyzing the objects here, in this case the trial section of the plate girder. I'm analyzing its rotation or bending about, or the stability analysis about this particular axis, the y axis. All right, so let us calculate this first, and let me repeat that the radius of gyration tells us that how far from the centroid the area is spread out, and a higher value of the radius of gyration will give, or will rather mean, that my structure is more stable against buckling. And here in this case I'm analyzing it from, or I'm taking stability analysis using the y axis, because I am interested to know about the bending or the rotation of this section, or checking the stability analysis of this section, or checking the stability analysis of this structure against the buckling, about which axis? The y-y axis. All right, so let's calculate the Iyy first. All right, so I'll be calculating Iyy. Listen carefully how I'll be calculating this Iyy. Now I may rub this. We don't need this hatch section. We use this to calculate the moment of inertia about the x-axis, but to calculate the moment of inertia about the y-y axis, I don't need this thing. So let me rewrite the dimensions. All right, so this is our same plate section, trial section of the plate girder, which is having a web of depth 1000 mm, thickness 10 mm, flange plates of width 400 mm, and thickness or height of how much? 25 mm. All right, now let's calculate moment of inertia about y-y axis. Listen carefully. This is the y-y axis, and now I'm calculating the moment of inertia. Same thing, or using the same geometrical formulas. This is a rectangle, so is this, and so is this. Now consider this rectangle, and this is the y-y axis. All right, this is the y-y. Listen carefully. This is the y-y axis, and I have to calculate I'll be calculating moment of inertia by calculating moment of inertia of this thing, and this thing. Then I'll sum them up, and then I'll have the moment of inertia of the whole I section about the y-y axis. Now listen carefully. This is the y-y axis. Now let's consider this flange first, the top flange. All right, this is a rectangular section. All right, and this is the y-y axis. Now I have to calculate the moment of inertia of this rectangle about the y-y axis. How much will be this? Now this is B, and now this is D. When I was calculating, or when I had to calculate the moment of inertia of the same rectangle about the x-axis, then this is the B and this is the D. Now that I'm calculating about the y-y axis, now this is B, this is D. All right, now let's calculate. How much is B? BD cube or BH cube by 12. So 25 multiplied by H. How much? 400 cube by 12. All right, now since the bottom flange also has the same dimensions and will be having the moment of inertia about the y axis same, B, that's 25, D cube by 12, so I'll multiply it by 2. This is the moment of inertia of this flange, top flange, and the bottom flange about y axis. To this, I have to add the moment of inertia of the web section about the y axis, so that I can get the moment of inertia of the whole I section about the y axis. Now let's calculate about y axis of this web section. This is the y axis. All right, this is the y axis, this is the web rectangle. All right, now tell me, what is the moment of inertia for the y axis? This is B, this is D. All right, this is the y axis, this is the web plate, so this is B now, and this is D. If I had to calculate about x-axis, then this was the B, this was the D. All right, BD cube by 12 about the y axis for the web plate area. How much? B 1000, D 10. B D cube by 12. All right, now by calculations, my Iyy is equal to how much? We'll be calculating, and by calculations it is equal to 2.66 into 10 raised power 8 mm raised power 4. All right, so this is the moment of inertia of the trial section of the plate girder about the y axis. Now comes radius of gyration, which we are denoting it by Ry. All right, in our elastic critical stress formula, we are denoting it by the term Ry, though sometimes it is also denoted in physics by K. right? So ry, it is equal to how much? Square root of I about yy divided by a. So one more thing we are requiring, that is a. Let me quickly show you here area. How can we calculate the area of this I section? By summating the area of the flange areas and then to the web areas. What is the area of this flange area? B into D or B into H. So 25 into 400 multiplied by 2, since both the flange areas have the same dimensions, plus I'll be summating to it, or I'll be adding to it what? The area of the web section. That is how much? 1000 into 10. These are the rectangular sections and the areas. So the area of my I section by calculation is 30,000 mm square. All right, I calculated the area of this flange area, 25 into 400. So is this 25 into 400, and it says 1000 into 10. I got my area. Now I have IYY, I have A. I can calculate my radius of gyration or radius of gyration, howsoever you may like to pronounce it. So it is IYY. How much did we calculate it? It's here 2.66 into 10 raised power 8 divided by area. It is 3 into 10 raised power 4, or let me write it down like so. By calculations, my radius of gyration is equal to 94.16 mm. All right, now I think I have every term that is to be used in the formula to calculate the elastic critical stress. I'll be substituting the values and I'll get my elastic critical stress. Then from the RC24 table, I'll be having my permissible or allowable working stress or the permissible bending stress. Then only I can say whether my section is safe against flexure or bending or not. Let us calculate the elastic critical stress first. All right. I'll be substituting the values in the elastic critical stress formula. Elastic critical stress is given by 2677300 divided by how much? L divided by Ry square of it into 1 plus 0.05 LTC divided by Ry multiplied by D square of it whole raised power 1 by 2, and the unit will be Newton per mm square. All right, now we have everything. We know the depth, we know the thickness, we know the radius of gyration. Now this thing, L. L is the effective length of the compression flange. And now if we are using cross bracing at the intervals of 5 meters, we have, or we are using cross bracing. We are using cross bracing at intervals of 5 meters. So our L will be, or the effective length of the compression flange will be 5000 mm. All right, now let's quickly move on and study first about the purpose of the cross bracings. All right, for longer spans, cross bracing is typically it's placed at every 3 to 6 meters along the bridge. I'll write it down for you. For longer spans, cross bracing is typically placed at every 3 to 6 meters along the bridge. All right, and it is usually placed at panel points in case of a truss bridge. Now let's see the diagram. This is the diagram of my Warren truss type steel truss bridge, which is having 6 panels of 5 meter each. 1, 2, 3, 4, 5, and 6. And how much is the panel area or panel point is at every 5 meters. 1, 2, 3, 4, and 5, and I'm having 6 panels of 5 meter each for my Warren truss, and these are my truss details. And the cross bracing for the longer spans is typically placed at every 3 to 6 meters along the bridge, and usually it is placed at panel points. So my every panel point is at 5 meters. So I'll be placing, or I'll be using, that's why I wrote it here, that I'll be using cross bracing it every 5 meters. Now how much is my L now? So the effective length of the compression flange is 5000 mm. Now I have every this value that I need to substitute in my elastic critical stress formula, and then I can calculate my elastic stress. Before calculating the elastic stress, let me tell you something very quickly about the purpose of cross bracings. Cross bracings are used for one, lateral stability, because it prevents buckling of compression members, especially the top chords. Second, load transfer. That is the purpose of using the cross bracings. It helps with load transfer. It distributes the wind, seismic, and other loads between trusses. 3. For torsional resistance, helps maintain the geometric integrity of the bridge. Torsional resistance. And it also helps in providing resistance to sway. Cross bracings, they also help to provide resistance to sway. That means it resists the wind, seismic, and other dynamic loads that are going to come on the bridge. That is the purpose of using the cross bracings. And for the longest spans, we typically brace them at every 3 to 6 meters along the bridge. And now, since we have a Warren truss stripe bridge, which is having 6 panels of 5 meters each, so we'll place our cross bracings at every panel point, that is after every 5 meters. All right, that makes the effective length of my compression flange as 5 meter or 5000 mm. Now I'll be calculating my elastic critical stress. All right, let me rub it first, and we'll be calculating the elastic critical stress. The procedure is same for designing a plate girder bridges. So by learning this, you're also learning how to design a plate girder bridges. Same to same. All right. Let us calculate now elastic critical stress by formula 2,677,300 divided by L. L is how much? 5000 divided by Ry. We calculated our radius of gyration as 94.16 mm. Square of it, 1 plus 0.05, then L, 5000, multiplied by TC, that is thickness of the compression flange. How much? 25, divided by Ry, or the radius of gyration, 94.16, multiplied by, in formula we have D. All right, D is how much? Depth of this whole I section is 1050, square of it, and whole raised by 1 by 2 Newton per mm square. By calculations, my elastic critical stress is 986.71 Newton per mm square. Alright, so by calculations, my elastic critical stress is how much? 986.71 Newton per mm square. Now, the allowable working stress or the permissible bending stress for different values of critical stresses are prescribed in the table as given by the IRC, and the permissible bending stress corresponding to the critical stress of 986 is how much? As given in the table, it is 149. Please see the table. This is the table. From here, elastic critical stress in Newton per mm squares. I have to check my allowable working stress or the permissible bending stress for the rolled steel sections having yield strength of 236 Newton per mm square. So I have to check this table, not this one. This is for different values of yield stresses like 299, 311, 331, and 362, etc. All right. How much is my elastic critical stress? 986.71. 980. See, here are two values, 900 and 1500. So it lies closer to this value, 900. 986.71 Newton per mm square is my elastic critical stress. All right, so I'll be checking it from table. It is closer to 900 rather than 1500. For 900, it is having a value of what is having a value of allowable working stress or the permissible bending stress is having a value of 149 Newton per mm square. So I'll be taking this 149 Newton per mm square. So for the elastic critical stress of 986.71 from the table IRC 24, I'm having my permissible bending stress or the permissible flexural stress or the allowable working stress as 149 Newton per mm square. All right, it is how much? Sigma BC, permissible or allowable. How much? 149 Newton per mm square. How much was the actual bending stress? Actual maximum bending stress was 144 Newton per mm square. So actual is this, permissible is this, hence the actual flexural stresses or the bending stresses are within safe permissible limits, hence safe. All right, since 149 Newton per mm square is greater than 144 Newton per mm square, that means my actual bending stresses are less than the permissible or the allowable bending stresses or the flexural stresses. Hence the actual flexural stresses, are within the safe permissible limits. These are within the safe permissible limits. Hence, the section is safe against bending or flexural stresses. All right. So this is how we calculate, or rather how we check our I sections for the maximum stresses or for the maximum bending stresses. All right. Now let's move on. Now we have to check our section for the shear stresses. All right. Let's see how we do it. Since we have completed the check for the maximum bending or the flexural stresses, now we have to check the section for the maximum shear stresses. All right, let me rub it first. This was rather a lengthy method of check, but nonetheless, we have to check anyway. All right, so the use of tables of IRC is very important because that's the core we are following for designing our bridges. All right. Average shear stress average shear stress is given by check for the maximum bending or the permissible bending or flexural stresses is complete. Now the shear stress part. Average shear stress is given by, it's presented by tau, and it's given as V into D into 10, where V is the shear force, D is the depth of the web, and 10 is the thickness of the web plate. All right, tau V. How much was my design shear force? It is 664 kilonewton. Dimensional homogeneity, D is 1000, and this is 10. All right, by calculations, average shear stress is 66.4 Newton per mm square. All right, So the average shear stress for this trial section of the blade girder is 66.4 Newton per mm square. I have to check it from the allowable average shear stress in stiffened webs of steel conforming to IRC 24. I have to check it for this is the average shear stress in this section. I have to check it from the table which gives the allowable average shear stress in stiffened web of steel conforming to IRC 24. All right, and this is the table. Let me show it to you first. This is the table which gives me the allowable average shear stresses in stiffened webs of steel conforming to IS 226, and this is the IRC table, and this gives me the shear stress. But for different distances between the stiffeners, it is based on that thing, distance between stiffeners. So first thing to calculate the allowable average shear stress is to know the distance between stiffeners. All right. Now let me rub it first, and step by step I'm showing it to you that how we are calculating, or rather how we are checking our section against various stresses, so that our section is safe against every form of stress, be it bending or flexure, or and shear stress, and then only we can proceed further. Now this permissible average shear stress depends upon the ratio d by d. D is 1000, d is 10, so this is 100. All right, and the stiffness spacing is given by 0.33 to 1.5 d. All right, stiffness spacing is given. We can choose stiffness spacing between 0.33 d to 1.5 d. All right, so using stiffness spacing, of, we can go from 0.33 to 1.5 d. Let us take 1d. That is how much? 1000 mm is the d. So I chose my stiffness spacing to be how much? D. All right, and another parameter that governs this allowable average shear stress is the ratio d by t. This is 100. All right, and this is the stiffness spacing. We used how much? We can choose anything, or we can rather use anything from 0.33d to 1.5d. We took it 1d. Our d is 1000 mm. All right, now we have to calculate it from the table. So this is the table. Two things it's dependent on: allowable average shear stress in stiffened webs of steel. It is dependent on ratio d by t, and it's dependent on the stiffness spacing. All right, here in this column it is the ratio d by t, and here from this side you can see various spacing of the stiffeners you are using. Then only you will be having some values of the allowable average shear stresses. All right, these are the spacing: 0.4d, 0.6d, 0.8d, d, 1.2d, 1.4d, or 1.5d. And as already discussed, we can choose stiffness spacing anywhere between 0.33d to 1.5d, and d being the depth of the web blade. All right, now for this section we chose 1d. That is 1 multiplied by the d is 1000 itself. That means we chose 1000. So this is the table we are interested in, or which will give me the allowable average shear stress. What is the second factor? D by T ratio. D by T ratio was 100. All right. Now the starting point we have here 110. We don't have 100. That means we have to check this and this. How much? It is 87. This is my d by t ratio, and this is the stiffness spacing I'm using. So I'll be checking it like this. For example, if my d by t ratio was 170 and my stiffness spacing was 0.80, then how much was my allowable average shear stress? It was 83. All right. Now my d by t ratio is 100, which is missing in the table. But anyway, the closest or the nearest one is 110, and my stiffness spacing is D. So I'll be checking this column. How much is it? 87 Newton per mm square. Please note that the allowable average shear stress, from RC table is how much it is. How much did we check? 110. In this column, stiffness spacing, we don't have 0.40, we don't have 0.60, we don't have 0.80, we have the D. So 87. 87 Newton per mm square. How much was the average shear stress? Average shear was how much? It was 66.4 Newton per mm square. All right. How much is the tau allowable? It is 87 Newton per mm square. Hence safe, because the average value of the shear stress for this section is less than or within the permissible range, because allowable is 87 and average in this section I'm having how much? 66.4. 66.4 Newton per mm square is less than 87 Newton per mm square. Hence, the section is safe against the shear stresses, because the allowable average shear stress in the stiffened web is more than the average shear stress that is for the design parameters of the shear force and the section I chose for my trial section. Hence, it's safe. All right. So the check for my flexural stresses is complete. So is the check for my shear stresses. Both are complete. Moving on. The next part of designing my cross girder is to design the connections between the flange and web. All right. Connections between flange and web. Once again, let's repeat. Permissible average shear stress was 87 Newton per mm square from the table. My average shear stress was 66.4 Newton. Hence, it was safe because my permissible average shear stress was more than what was the actual average shear stress here in the trial section of plate girder. All right, next step is connections. Connections between flange and web. Flange and web need to be connected by welding or the welds. Now we'll be assuming, or we'll be checking for what size of the weld we'll be using, so that the strength parameters remain, they're not compromised, and the connections between the flange and the web are designed in a proper way. Now the connections between flange and web is designed to resist a maximum horizontal shear force, which is given by all right, we are designing the connections between flange and the web. All right, and these flanges and web need to be connected by welds. All right, And the connections between flange and web is designed to resist a maximum horizontal shear force which is given by this thing. I'll write it down. The connections between flange and web is designed to resist a maximum horizontal shear force, given by tau is equal to VA y bar divided by I. All right, where V is the shear force at the section, A is the area of the flange, y bar is the distance of the centroid of area from neutral axis, and I is the moment of inertia about the x-axis. All right, so let us substitute the values and we'll be having the maximum shear force at the junction of web and flange here. All right, let me substitute the values. Because the connections between flange and web is designed to resist a maximum horizontal shear force, which is given by this formula. And let me substitute the values. So this sum T or tau, however you may like to write it. So let me write it as this. And how much is my design shear force? 664 kilonewton into 10 raised power 3. How much is the area of the flange? 400 into 25. I am calculating maximum shear force at the junction of web and flange. Maximum shear force at the junction of flange and web. Because I'm designing the connection between flange and web. So the maximum shear force at the junction of flange and web is given by this formula. Let us substitute the values. Please ignore this. 664 into 10 raised power 3 is design shear force, or the shear force at the section. A is the area of the flange. It is 400 into 25. Y bar is the distance of the centroid of area from the neutral axis. How much is that? This is 1025 divided by 2. All right. Y bar is the distance of the centroid of area from the neutral axis, and that will be equal to 1025 divided by 2. 1025 divided by 2 is the distance of the centroid of area from the neutral axis. All right, and that is equal to how much? 512.5 mm. 512.5 mm. Right, divided by I, xx. We already calculated it, 61 into 10 raised power 8 mm raised power 4. All right, so this is the maximum shear force at the junction of the flange and the web for designing the connections between flange and web, and this is given by this. And already discussed, the connections between flange and web is designed to resist a maximum horizontal shear force, which is given by this formula. All right, I substituted the values for the shear force, the area of the flange, the distance of the centroid of area from the neutral axis, which was 1025 divided by 2. This is the web, this is the flange. All right, we are discussing, or we are designing, or we are checking the maximum shear force at the junction of the web and flange. So this is flange, this is web. How much is the total depth? 1025. This is 1000 and this is 25. 1025. We have to divide it by 2. We divided it by 2. That was 512.5. That is why we take it 1025 and we didn't consider the whole 1050. All right, because we are checking the connections, or we are designing the connections between flange and web, and we are checking for the maximum shear force at the junction of the flange and the web. So we took, or if we'll be designing it from here to here, only one, all right? 1025. 1025 divided by 2. I hope it's clear to you. Now by calculations, my maximum shear force at the junction of the flange and the web is equal to 557.86 Newton per mm square. This is the maximum shear force at the junction of the flange and web. Now I'll show you how we take this value and from the tables as given by the IRCs, how do we select various welds and their size. All right.